Bismillahirrahmanirrahim. BS Physics, Semester 1, Mechanics Course Code 1103, Chapter number 7 and the second lecture in Chapter 7, overall 22 lecture. The chapter name is Energy and Energy Transformation. The name of this lecture is Work Done by Variable Force and Work Done by a Spring. Dear students, I am talking to you, Rashmat Ali, Assistant Professor of Physics, Khwaja Farid, Government Postgraduate College, Rimia Khan. The material of this lecture has been taken from the physics for the scientists and the engineers by Survey Javed, and the second one is the Fundamental Physics by Halliday and Resnick, also by Gerald Walker. We can see the main title figure of the chapter as the windmill. There are two articles in this lecture: work done by variable force, and other is the work done by spring. Means work done by spring is an example of variable force. Work done is a conditioned parameter. That is, we know about the work done in the previous lecture. That is the scalar product of force and displacement. If both are along the same direction, then there will be only two quantities. And if force and displacement are not along the same direction, then there must be three quantities by which we can evaluate, find out the work done. The third quantity will also be angle theta. So, theta is conditionary. Force and displacement, two variables. When a force acts on a body, displacement varies, work is to be done. Here, conditions are applied on the force, nature of force. So, we can divide the work in the two types. One is the work done by a constant force that we have studied in the previous lecture, lecture number 1 of this chapter. Another is the work done by a constant variable force. First of all, we have to know about the difference constant force and variable force. If a force means its magnitude and direction remains same at all instants, it's a constant. But if a force that changes from point to point with time is known as variable force. There are so many examples. First example is the spring force. As we know that if a spring is tied to a support from one side and force is applied from the other side, as we apply a force, extension or compression will be produced. In other words, deformation will be produced. This deformation depends upon the force. As the force increases, deformation also increases. As the force decreases, deformation also decreases. So, this force acting on the spring is a spring force, and the force is variable. Similarly, the other example is the force of gravity. That is, if we place somebody in open air, the force of gravity weight acts on it and pulls towards the center of Earth. As we move from Earth's surface to high up above the Earth's surface, the force of gravity varies. It decreases from surface to infinite distance. Similarly, the force acting on a body moving along a curved path, on the curved path, the direction of force changes as well as the magnitude changes. These are the three examples of variable force. So, we will find the work done by the variable force. For this, consider a particle being displaced along x-axis or horizontal under the action of force that varies with position. The particle is displaced in the direction of increasing positive x from x equal to xi to x equal to xf. So, if we see that, then we should have to apply the formula of work as we have studied in the previous lecture. That is, W is equal to F delta R cos theta. Perhaps we cannot apply in this situation this formula, because this formula is used to calculate the work for constant force. But in this case, the force is not constant. So, we have to apply the strategy that the displacement covered should be divided into small interval. Such a small interval, the force F becomes nearly constant in each interval of displacement. Then we can apply this formula. So we see this formula W is equal to F delta R cos theta to calculate the work done by the force, because this relationship applies only when F is constant and in magnitude and direction. However, imagine that the particle undergoes a displacement delta x shown in the figure. The x component of force Fx of the force is approximately constant over this small interval. For this small interval, we can apply the formula approximate to the work done. Work done would be equal to Fx delta x. This work, because Fx and delta x are in the same direction. If we see the diagram, delta x graphically is taken along the x-axis and Fx is taken along the y-axis, because Fx is dependent. We have divided the whole path into small intervals, each of length delta x, and see that the force is approximately constant in each interval. So, first, how to find the work done? We use the area method here, because directly force is to somewhat variable. The area method is The area shaded under F and delta X region represents the work. As work is F and delta X, so this forms a area. Area means length of this rectangle and the breadth of rectangle, as length represents the force and breadth represents the displacement. So area of the rectangle gives the work done. For this, area formula is shown here. Delta A equal to Fx, and delta X as Fx is the length of the rectangle and delta X is the width of the rectangle. The shaded area shows the work done in this case. This is work done for a small element, small interval, small displacement. As we have divided the whole path into small displacements, if we want to take the total work, then we will add the work done by the force in each interval, in each delta X. F is approximately same in a single delta X, but it may vary from one interval to another interval. So, for the total work done from initial position xi to final position xf, we take the sum of work done in each interval, each element. This is work, we can say that sigma xi to xf fx delta x. If the size of the displacement is allowed to approach to 0, size of displacement is allowed to approach 0, the number of terms in sum increases without limit, but the value of the sum approaches to a definite value equal to the area bounded by the fx. So, taking the sum, if we see that delta x is approaching to 0, the interval will be so small that sigma can be converted into the integral sum from initial to final. This is the work done by variable force. So, general result, therefore we can express the work done by Fx as the particle moves from xi to xf, as shown in the figure. W is equal to integral xi to xf fx and delta x dx. This will be the area of the area under the force displacement graph, as we can see from the figure. This equation reduces to previous equation when component fx equal to f cos it as a constant. If more than one force acts on a system, and the system can be modeled as a particle, the total work done on the system is just the work done by the net force. If we express the net force in the positive x direction as positive fx, then the total work done or the net work done can be written sigma w net work done, sum of all the forces we have included in it. If the system cannot be modeled as a particle, for example, if the system consists of multiple particles that can move with respect to each other, we cannot use the above equation. This is because different forces on the system may move through different displacements. In this case, we must evaluate the work done by each force separately and then add the work algebraically. So, the second article of this lecture is the work done by a spring. As we have learned, the work done by spring is an example of variable force. A model of a common physical system for which the force varies with position is shown in the figure. We can see from the figure a mass spring system on a horizontal frictionless surface. The first figure A, x is equal to 0, the body is in equilibrium, and when we apply a force towards right, displacement x is moved, the spring is extended, and here x is positive, and we see the fx is written as a negative because this points to the restoring force. So a model of common physical system for which the force varies with position is shown in the figure. A block on the horizontal and frictionless surface is connected to a spring. If the spring is either stretched or compressed a small distance from its unstretched equilibrium configuration, it exerts a force on the block as expressed by Fs equal to minus Kx, where negative sign shows that the restoring force that brings the body back to its initial position, and Kx is the spring force, variable force. Here we can see that x, position of the block relative to its equilibrium position, x equal to 0 position, k, a positive constant called the force constant or the spring constant of the spring. In other words, the force required to stretch or compress a spring is proportional to the amount of stretch or compression x. This force law for spring is known as Hooke's law. The value of K is measure of stiffness of spring. Stiff springs have large K values and the soft springs have small K values. The unit of K can be written from the formula Newton per meter. The negative sign signifies that the force exerted by the spring is always directed opposite to the displacement, that is towards equilibrium. X is always directed away from the equilibrium and force is always towards the equilibrium. Since the spring force always acts towards the equilibrium position, x equal to 0, it is sometimes called the restoring force. If the spring is compressed until the block is at a point and x maximum, point 0 and x maximum, and it is released, then block moves from x maximum through the 0 to x maximum. If the spring is instead stretched until the block is at the point 0 to maximum, it then reverses direction and returns to x maximum and continues oscillating back and forth. So this situation is shown. Initially the body is equilibrium, we can see at the point B. Second step, force rightward is acting on it, then restoring force pulls back to the mean position. When body comes to the mean position, inertia takes it to the other position, new position in figure C, and again restoring force comes in action and brings back to the mean position. In this way, the mass spring oscillates and the work can be calculated from its activity. Now, we are interested to find the work done. Suppose the block as a system has been pushed to the left to a position that is x maximum, and it then released. To calculate the work done Ws from xi to xm maximum, again to xf to 0, applying the above equation, assuming the block as a particle, we can take the work as Ws equal to x integration xi to xf fs dx. We have started the motion from extreme to mean position, that is here written minus x to 0, putting the value of fx, so we will take final get the result as 1 by 2 kx maximum square. Here the formula of derivation integration is written here. If there is some variable having power n, then its integration is the adding 1 power to the power 1 to the power and then the whole power at its denominator. If n is equal to 1, we can see easily the result as evaluated in the formula. The work done by the spring force is positive because force and displacement both are to the right. The block arrives at x equal to 0. With some speed, it will continue moving until it reaches a position x maximum on the other side. When we consider the work done by the spring force as the block moves from xi 0 to xf x maximum, we find Ws equal to 1 by 2 kx maximum square, because for this part of the motion of the displacement is to be to the right and the spring is to the left. Therefore, the net work done by the spring force as the block moves from xi 0 to xf, that is the x maximum is 0. So the work done calculated in the equation is the area of the shaded triangle corresponding to 1 by 2 kx maximum square of the displacement from x maximum to 0, because the triangle has a base x maximum and the height area is the work done by the spring as given above equation. See in the figure, if body moves towards right, x becomes positive, whereas fs becomes negative. If the body moves from extreme right to 0, then x becomes negative and similarly the work done from xi, x equal to xi to xf, we can write it as, this is the formula for the change in work done. We take an example. If the spring has a force constant of 80 Newton per meter and is compressed 3 centimeter from the equilibrium, the work done by the spring force as the block moves from xi 0 to xf, x maximum 3 centimeter to its unstretched position, xf equal to 0, so 3.6 multiplied 10 to the power 2 joules. This work is equal equal to the negative of work done by the spring for this displacement. Work done by applied force 0 to x maximum, F applied dx, and F applied is equal to kx because F applied is always positive, evaluating 1 by 2 kx maximum scale. Similarly, the work done by an applied force on a block spring system between the arbitrary positions, we can write it as F applied xi to xf integral form dx F applied dx. Putting the values, we get the work done at an instant in this form. Notice that this is the negative of the work done by the spring as expressed by the equation. This is consistent with the fact that the spring force and the applied force are of equal magnitude, a system, but in opposite directions. This is the work done by applied force. We can see that applied force is towards the right and the restoring force is towards the left in the equilibrium position to x maximum. Thanks for listening and focusing with patience. Allah bless you all. Allah Hafiz.